Swayam Prabha. Digital India. Educated India.
Let's get started with our discussion on the relation between properties on thermodynamics. So, that is a very important question, and I already mentioned that one of the primary aims of thermodynamics is to establish the relation between properties. So, to that end, we would like to discuss another issue of pressure volume relation under adiabatic condition. We know that in the case of isothermal condition, you get the relation between PV equal to constant under isothermal condition, and that you know almost from your school days, and that is a very important defining relation that you all know, that is the Boyle's law, and but that is in isothermal condition, that is important. Now, if we try to seek a relation between the pressure and volume under a different condition, that is, you are changing pressure with volume, then what should be the relation under adiabatic condition? So, that's what is the relation? So, what is P versus T under adiabatic condition? So, for this, what we will do, we will consider a case of expansion under adiabatic condition, adiabatic but reversible expansion. So, we will consider an adiabatic at the same time reversible expansion of a gas in which we consider ideality, that is an ideal gas, reversible expansion of an ideal gas. Expansion of an ideal gas. So, that is the thing that we are going to pursue, but for that we again start from our basic equation, the first law of thermodynamics. So, first law of thermodynamics tells us that if dq amount of heat enters into the system, then it increases the internal energy by an amount dE, and if dW amount of work is done by the system, then it is dE plus dW. So, this is from the first law that we know. Now, under adiabatic condition, so under adiabatic condition tells us that dq is equal to 0, So, the equation is basically Cv dE or dE equal to minus dW, and dW is a mechanical work, which is P opposing times dV, the change in volume. So, this is the relation, and now Cv dE is something that we can express energy as a function of temperature and volume. So this is del T at constant volume times dt plus del V at constant temperature times dV, that is equal to minus P opposing times dV. And so, since we are considering an ideal gas, for ideal gas tells us that is del E del V at constant temperature, that is equal to 0. That is from Joule's experiment. And so we can forget about this term, and the term that we have is Cv. It is basically Cv del E del T Cv times dt, that is equal to minus of P opposing times dV. And since it is under reversible change, since it is reversible, means at all throughout the change we have maintained an equilibrium condition with the surrounding. So that means some reversibility implies P opposing equal to the P pressure of the gas, and that gives me Cv dt equal to minus P dV, and P I can replace because the gas is ideal. I can write P equal to RT by V for 1 mole of ideal gas. So all these conditions are being fulfilled here, and so what I can write is that Cv dt equal to minus RT by V times dV. So we slightly rearrange this equation in this form, that is dt, put this t here as a denominator on this side, and that is equal to minus R by Cv, and this is dV by V. So that is the rearranged equation, and this is the result of the change of V with change of T. So this is a pressure, a volume temperature relation, and we just work out a little bit about around this R by Cv in this way. We know for ideal gas, we have shown that Cp minus Cv equal to R. So if I divide both sides by Cv, that is Cp by Cv minus 1, that is equal to R by Cv. So R by Cv can be replaced by this one, and this I may write as gamma minus 1. Since Cp is always greater than Cv, that is the point that to be noted, because when your volume is fixed, so the heat energy that you are giving to the system is completely only employed to increase the internal energy, but when under constant pressure condition, so that heat also goes to the expansion mode or work mode, so it can take more energy. So Cp is always greater than Cv, and that gamma is greater than 1. So that is the usual standard notation that we are using, and therefore, and this quantity is d of log to the base E ln T, and that is equal to minus gamma minus 1 to the power ln V, or you may write it as ln T d ln T equal to 1, if you write it 1 minus gamma, that is ln d ln V to the power 1 minus gamma. So, this is the relation. Then if you integrate between T1 to T2, some d, yes, means that d ln V. So, this is d ln T to d ln V to the power 1 minus gamma. So, once you know this, then I can integrate and see that this is ln, say, between two temperature ln T2 by T1. So, if you integrate between the two temperatures T1 to T2, and it is ln V2 by V1 to the power 1 minus gamma. So, it is obvious that T2 by T1 equal to V2 to the power 1 minus gamma divided by V1 to the power 1 minus gamma. So, may slightly rearrange it, is the T2 by T2 to the power 1 minus gamma equal to, that is T1 by V1 to the power 1 minus gamma. So, or you may write it as T2 V2 to the power gamma minus 1 equal to T1 V1 to the power gamma minus 1. So, this is a very simple relation, and if I want to find out the relation between the pressure and volume, and for the ideal gas, I will replace this T1 by T2 by, so T2 by T1 for the ideal gas, this is P T2 by T1, that is basically RR cancels out, it is V1. So, I may write it P1 V1 by T1 equal to P2 V2 by T2. So, T2 by T1 is basically, so T2 by T1 is basically P2 V2 by P1 V1. So, that means I can replace this T2 by T1 for ideal gas again, and then T2 by T1 is basically P2 V2 by P2 V2 to the power times V2 to the power gamma minus 1 equal to P1 V1 to the power gamma minus 1 into gamma 1, and that gives me the cancellation of this one. So, P2 V2 to the power gamma equal to P1 V1 to the power gamma, or P V gamma equal to a constant in general. So, this is the relation that we could establish only because the fact that we started from an equation from the first law of thermodynamics. So, it is one of the consequences of the first law of thermodynamics, and that gives us a clear relation between the pressure and volume when we change the gas under adiabatic condition, a reversible adiabatic condition. Please remember that reversibility condition is also important, otherwise could not replace this the P opposing equal to P. That's the important point. And so that pressure volume relation is completely different from what is known for the ideal gas and what is known for the isothermal condition. So if you compare the gas line between the pressure volume curve, in this case you will see that we get the P for this particular isothermal condition. P varies as 1 by V, is basically a rectangular hyperbola kind of thing, and this is for isothermal condition, the pressure volume relation. And because of this gamma term, and which is larger than 1, so pressure varies as 1 by V to the power gamma, and that curve becomes slightly steeper, relatively a steep line. So this variation is 1 by V for this case, and for this case the variation is 1 by V to the power gamma, with gamma greater than 1. So in this case, for adiabatic case, so this is for adiabatic case, and that was for the isothermal case. So there are differences between the P pressure volume relations and the isothermal condition and adiabatic conditions. So this is one of the standard results that can be found in any textbook on thermodynamics, but that gives us a very important relation between pressure and volume, as simple as that. With respect to another property, that property of Cp by Cv. So these pressure and volume are the course of properties that you specify for the gas. You keep the gas at some pressure and it has a different volume, but this appearance of gamma, that means it is a ratio of Cp by Cv, means that it is also connected to the other detailed thermal properties of the gas, that is specific heat at constant pressure and specific heat at constant volume. So that's a very interesting relation that we need to know about. And so far so good. Now this is another relation that we established. So that was the second topic that we actually covered, and then finally, to conclude this applicational part, a simple application part and consequences out of first law, we will try to establish another relation. This is a relation between pressure and volume. So in general, what is the relation between the three parameters: pressure, volume, temperature? So this is a relation between pressure and volume, all that we discussed just now. And next we go over to the another relation, the relation between the pressure, volume, and relation between temperature. So what is the relation? Because these parameters are important to specify typical thermodynamic system, and so we now consider that just the three variables instead of pressure, volume, temperature. We first consider that there are three variables x, y, z. So let us take take in general x, y, z such that z is equal to is a function of x and y. So, if this is so, z is a function of x and y. So, correspondingly, I can write x is a function of y and z and so on. So, dz equal to del z del x at constant y times dx plus del z del y at constant x times dy. So, if you write this, if you not just take that dz equal to 0, take dz equal to 0, then what happens that del z del x y dx plus del z del y at x dy equal to 0. And if you write, that means z is a constant, so I write it in a slightly different form, del z del x y constant, then del x del y under constant z, because dz equal to 0 implies z is a constant. So, we divide by dy, so dx dy, I write it partial derivative and that is with z constant plus del z del y x that is equal to 0. So, to write it slightly in a different form, del z del x at y times del x del y at z, then what we do, we write it here del z del y at constant x, then what I write now del y del x at constant del y del z at constant x. We multiply this with del y del z and that is equal to 0. And again, when I multiplied this with this term, so I will also multiply del y del z with x. So, it means that we have multiplied both sides by del y del z. So, del y del z at constant x on both sides, on both these two terms on the left hand side. So, this is the relation and you can see that del z del y and del y del z, they actually become ultimately 1, and there is a symmetry in this relation, which is z differentiating with respect to x and that constant y, and that is x or with y and at a constant z, y we differentiated with s z and a constant x. So, there is a symmetry in the relation and z del x y del x del y z del y del z at x plus this is 1, this is just 1. So, I take it the 1 on the other side, so it is minus 1. So, this is a very interesting and simple relation, and this is just a cyclic rule that allows us to establish a relation between x, y, z as a partial derivative. So, the product of partial derivatives. So, if I now identify, say, So if I identify Z equal to pressure and then say X equivalent to temperature and Y effectively this is a volume. So I can write it as follows: del Z, that is del P del T at constant volume times del T del V at constant P and del Y del V del Z at constant X means at constant T, that is equal to minus Y. So we have got a relation between pressure, volume and temperature, Pt, Tv, Vp. So Vp. So that's a cyclic rule. And now if these two derivatives can be expressed in terms of some known coefficients, so that is easier to and from that I can find out this particular quantity. So if I write that 1 by V, if I write that del V del T, that is the volume expansion, rate of change of volume respect to temperature divided 1 by V. If I write it, the coefficient of volume expansion alpha, if I write it alpha, that is the coefficient volume expansion, and del V del P, that when you increase the pressure, what happens to the volume? The volume decreases. So it will be better if I define that del V del P 1 by V, that is with the minus sign, that gives me a quantity, say it is, I call it kappa, and kappa is the compressibility factor, because this factor shows how much the substance is compressible, how much the gas liquid is compressible. So this is compressibility factor, compressibility factor, and if I now put this del V del T, so at a constant pressure and this is at constant temperature, this is at constant pressure, then this quantity turns out to be the following. So del P del T at constant volume times this. So I write this del V del T. So del V del T at constant pressure equal to alpha times V, or this quantity del T del V must be 1 by alpha times V. And so del V del, what is the del V del P? Del V del P is kappa times V, and there is a minus sign that cancels out. So minus times kappa E times kappa minus kappa times V, that is equal to minus 1. So minus cancels out, V cancels out, and you have del P del T at constant V equal to alpha by kappa, that is coefficient of thermal expansion divided by compressibility factor. So coefficient of thermal expansion divided by compressibility factor. So this is an interesting relation that we could establish purely from a cyclic rule. That cyclic rule actually uses the concept of the coefficient of thermal expansion and as well as compressibility factor. So this is basically volume expansion is thermal due to temperature, the thermal expansion. So effectively this is a relation that we could establish. So basically it is also again a relation between the properties. It is a property of the system, it is another property, this is another property. So two properties are related in this way. So whenever we have a pressure derivative of a pressure with respect to temperature at a constant volume, I can replace this by the ratio of these two quantities. That I can do. So these are the relations that we can derive for many other situations, and also for instead of ideal gases we go over to real gases, and of course the complications will emerge because of the fact that there are parameters to define the non-ideality for the specific gases and so on. So, but these are in nutshell the essential relations that with which we work in thermodynamics. So, thank you all, and next lecture we will move on to this another law, the second law of thermodynamics. Thank you all for your attention.